Winning a contest is quite difficult, but if you play your cards right, you always give yourself a chance to win. Today we are going to dive deeper and talk about how to select the perfect project and bring your ideas from paper to reality. But currently I'm fascinated by various wireless protocols because of the projects on which I'm working. So I'm connecting this interest with the contest and creating a wireless sensor network for environmental and energy monitoring. I know the name is quite mouthful, but my goal is to mainly deploy this in an agricultural field or a greenhouse, where I can effectively monitor different parameters such as crop health, temperature, humidity, soil health, and energy consumption of equipments used around this area. And by collecting all this data, we can optimally use the resource, which in turn saves energy. And by using this collected data, we can train ML models to suggest different crops that's suitable for growth without any additional fertilizers. While the concept might sound simple, the complexity of the project really lies in choosing the right components and the functionality while keeping the cost as low as possible. Also, we have to think deeply how the device can be made suitable for both indoor and outdoor data collection without compromising on the feature or making it very expensive. Anyway, since the project has been selected, I want to show my version of taking a concept into an actual product. But remember, this process can vary from person to person, so here's mine. Once I have the project idea, I usually do a process called memory dump. I just dump all my ideas and features that my project should have on top of the core functionality. Here you can go wild and come up with random features that you like, features from existing device on the market, or features from some academic paper that's recently published. And just like that, in a few hours, I have a huge list of things that I can implement in my wireless sensor network. Here you can see for slave nodes, I had ideas like using different form of energy harvesting methods and low power electronics and reading data from a wide range of sensors. Similarly, I had more ideas for master nodes, like using edge computing and some sort of tiny ML to produce results in real time rather than producing them in the cloud. Even though the most of these ideas sounds good, unfortunately it's hard to implement all of this at once because of our time and cost constraints. So we need to organize the features and shortlist some of them that will go into the final project. Typically for a wireless sensor network, these are the core features we need to have. For the slave node, we need to have a processor to read the sensor data, a wireless protocol to send the data wirelessly. Similarly, if I look into the core feature for the master node, I need to implement the same wireless protocol that's implemented on the slave to read the data and an interface to process the sensor data and send it to a cloud platform. Once we understand the core functionality of a project, we can shortlist more features from the memory dump while considering the cost and the time required to implement them. For example, in the slave node, I chose this additional feature along with the core features. First, a battery to power the slave, which will help in moving the slave device around. Then having an inbuilt RS485, as many industrial and agricultural sensors use them by default. It's a nice touch if the device has the port to read it by default. Since I'm planning to use the system both indoors and outdoors, I have plans to add as many ways to power the slave and also charge the battery at the same time, either by using a DC jack, USB-C, or by using a terminal block. Then finally, having an adjustable boost converter to convert the battery voltage to required voltage for various sensors that's available in the market. Similarly, I shortlisted few more things for the master node. So I made sure it can handle a wide range of input because most of the industrial devices run on a voltage between 12 to 24 volts. Then I made sure to add a robust power protection system to avoid fluctuation, overcurrent, transient voltage and reverse current protection. Then I thought I should have an option for local processing, just in case if there is no possibility of connection to internet. So I've included a buck converter which will convert the 12 to 24 volts into 5 volt 2 amp for a Raspberry Pi Zero, which can do all the processing locally. Just like the slave, I'll also include a RS485 driver in the master node to communicate with other host devices on site, like maybe a PLC or other industrial host systems. Now for both the master and slave, I have included two more additional features. First, I want to expose some of the GPIO pins for external circuits like controlling servo or stepper motors, which can be used for irrigation control, solar panel direction, etc. And finally, I've included a RGB LED as an indicator instead of having some fancy little display. From the final feature list, we can see there are quite a few things that's common to slave and master. So let's start with finding the components for those features. Starting with the wireless communication protocol. As I would like to implement the system both indoors and outdoors, LoRa would be the best choice. It consumes less power and also can transfer data over multiple kilometers, which is perfect for battery-based slave module. Here, you need to note something. The LoRa is just a wireless protocol, and there are many manufacturers who make this LoRa based IC and the module. So we need to shortlist the selection of the LoRa module or the IC that is going to go into our circuit. First, I need to find a LoRa module that's legal to use in my country. In this case, I need to search for a radio frequency of 868 MHz, and this can totally vary from country to country. So make sure to check with your country regulations before you start working with LoRa. Once I understood what the frequency range should be, then I needed to find a module that I can easily source and at the same time cost effective. So finally, after some research, I finally settled on this LoRa module, which satisfies all my requirements. Once the wireless protocol and the module is selected, I need to find a suitable microcontroller to fetch the data from the sensor and send it through the LoRa. In this case, I chose ESP32-C3 Mini and ESP32H2 Mini. I know, there are more energy efficient ICs and cheaper microcontrollers which I can interface with LoRa, which will definitely bring down the cost of slave and master nodes. But trust me, there are two specific reasons why I chose this IC. First, they are drop-in replacement for each other, which means you can replace one with the other and they would still work. So in a long run, this will help me in case I fall into supply chain issues. Secondly, the C3 Mini comes with a built-in Wi-Fi and Bluetooth support, which can be utilized when deciding to use the slave node as an independent device where it can still send the data directly to the cloud using the Wi-Fi. As for the H2 Mini, it supports additional protocols like Matter, Zigbee and Thread. This means the slave node can support multiple protocols at the same time, allowing it to integrate with other smart devices that are installed in the existing system. Next, for the RS485 protocol, I did not want some complex circuit, so I want to keep things very simple and just use the very popular MAX485 IC, which is used in a lot of devices because it's cost effective and easy to procure. With this, we have selected the components that can be used for both the master and the slave nodes. Now let's quickly find the other components that we need in the slave node. For the battery, I did a rough calculation on how much power the system might consume during sleep and while transmitting. So according to that, I selected a battery of 2200 mAh, and the slave node should approximately last for 3 to 4 days in a single charge. However, changing the battery this often isn't very practical. That's the reason we have solar panels on our feature list. Technically speaking, it's a little complicated to have both a solar-based charger and an external charger. It makes the circuit a little bit complicated. But I came across Adafruit circuit based on BQ24074 IC that is simple and easy to use. This IC allows the maximum power from the solar panel to the battery without using the maximum power point tracking. At the same time, it gives a wide range of input options to charge the battery and also run the circuit with external power. It might feel like I'm talking a lot of gibberish here, but I'll make sure to give a link in the description that talks more about this circuit in detail. Finally, to finish the component selection for the slave, I'll use the MT3609 SMPS circuit to generate a variable power supply for sensors that I'm planning to use. Now coming back to the master node, it has its own set of features. Unlike the slave node, the master node doesn't need a battery. Instead, if the master is powered down, we can make the slave hold the data temporarily and send it back when the power is back on. So we can do a lot of cost saving in the master node. And for the other feature, we need to find components that can take a wide range of input from 12 to 24 volts and produce a 5 volt 2 amp power to the external devices. And for this, I chose LM2596S. Just because I've used them in the past, it's low cost and it's very easy to procure. And that finishes the components required for the master node. Then apart from this main components, then there are a few more components I chose for both slave and master node, like the capacitor, resistor and linear regulators to keep the system stable, and a WS2812B RGB LED for the indication. Once I had all the components in place, I had to just do proper research on each of the components and get their data sheet. Along with that, I've also downloaded their symbol, footprint and 3D models that I can use in the CAD design. But this video is getting a bit longer than expected, so we'll stop it here for now. And if you have any questions or doubts so far, please don't hesitate to ask in PCB Cupid Q&A section. Also make sure you have liked and subscribed to this channel, because in the next video we'll see how we can convert this into a full-fledged PCB and send it for manufacturing. Until then, keep learning and keep creating.